In this video, I want to do a couple of examples of limits that involve the inverse tan function. So recall from class that I said it was important for you to know what the graph of tan inverse x looks like. So it's important for this class as well as for your future math classes. So here is what the graph of tan inverse x looks like. In particular, if you know what the graph of y equals tan inverse x it looks like, you'll know that the limit as x tends to infinity of tan inverse x is pi by 2. In other words, as x becomes large and positive, tan inverse x has tan inverse x approaches pi over 2, and the limit as x tends to minus infinity of tan inverse x is minus pi by 2. So you can see that here. Okay, so with this knowledge, we're going to do a couple of examples. So, first example, A. So, what is it? So, in this example, we're supposed to calculate the limit as x tends to minus infinity of tan inverse of x to the fourth minus x cubed all over 2x squared minus 7. All right. So for this, let's first calculate the limit of the argument of tan inverse here. So let's calculate the limit of x to the fourth minus x cubed over 2x squared minus 7. So to do that, well, we can use our general method for evaluating limits at infinity, which involve a polynomial over another polynomial. All right, so what can we do? Well, we know that when evaluating this limit, in this case at minus infinity, we can just drop all lower powers of x from both the numerator and the denominator. So this is going to be the limit as x tends to minus infinity of x to the fourth over 2x squared. And canceling x squared from this, we have the limit as x tends to infinity of x squared over 2, and it should be clear that this is equal to infinity because, well, as x becomes large and negative, x squared is going to become large and positive. Divide that by 2, you're still going to have large positive values, arbitrarily large positive values, in fact. So the limit is equal to infinity. All right, so looking here then, what can we say? Well, this bit that we've circled here, we know is tending to infinity as x tends to minus infinity. All right, so what do we have? So we're taking the limit as x tends to minus infinity, tan inverse of this function here. And what we've determined so far is that as x becomes large and negative, this, the argument of tan inverse in this case, is going to become large and positive. So what does tan inverse of a large positive number look like? Well, we know from up here, which we know from the graph of tan inverse, that as x becomes large and positive, tan inverse x becomes close to pi by 2. In other words, tan inverse of large positive numbers are close to pi by 2. So what's this limit then? Well, this limit is itself going to be pi by 2. So let's write that down. So equal to pi by 2. And that's it. Okay, for our next example, we want to calculate the limit as x tends to 0 from the right of tan inverse of log x. Okay, so for this one, we are going to want to use our knowledge about the graph of the inverse tan function, but also our knowledge of the natural logarithm function. In particular, what does the graph of the natural log function look like? It looks like this. So, step to the side. Remember that the natural log function y equal to log x looks like this, and in particular, what do we know? We know that as x tends to 0 from the right of log x is minus infinity. So, looking at the picture, as x tends to 0 from the right, in other words, as x is approaching 0 from the right, what happens to the log function? Well, the log function becomes large and negative. So this limit is equal to minus infinity. Okay, so coming up here, what do we know? The limit as x tends to 0 from the right of tan inverse log x, well, what's happening to this log x? As x gets close to 0 and x is bigger than 0, well, this log x is becoming arbitrarily large and negative. That's what we just said. So I'm just going to indicate that here. So, as we said, this is tending to minus infinity. But what is tan inverse of a large negative number? Well, if we go up here to our graph of tan inverse x, we know that tan inverse of large negative numbers, so tan inverse of large negative numbers are always, the tan inverse of a large negative number is going to be close to minus pi by 2. In other words, as we wrote here, the limit as x tends to minus infinity of tan inverse x is equal to minus pi by 2. So, what can we say? As we just said, as x approaches 0 from the right, we're taking tan inverse of large negative values. Tan inverse of a large negative value is going to be close to minus pi by 2. We can conclude that this limit here is equal to minus pi over 2. Okay. And now for our last example, we have the limit as x tends to infinity of tan inverse 7x squared minus x all over x to the 4th plus 3x squared. So, again, we'll start by examining the limit as x tends to infinity of the argument of the inverse tan function. So what do we have there? So let's just check. So the limit as x tends to infinity of 7x squared minus x over x to the 4th plus 3x squared. Well, we have a rational function here, a polynomial over a polynomial. So, as usual with limits at infinity of this type, we can just drop all lower powers of x from the numerator and the denominator. And we're left with this limit here, which, after canceling x squared looks like the limit as x tends to infinity of 7 over x squared, and this limit is equal to 0. As x becomes large and positive, 7 over x squared becomes close to 0. So what have we shown? Shown that this argument here is tending to 0 as x tends to infinity. So what does that mean? It means that the limit as x tends to infinity of tan inverse of this function here is just going to equal tan inverse of 0. So write that down. And now it's just a question of figuring out what tan inverse of 0 is. So let's do that down below as well. Okay, so let's see. So down below, let's notice that what does it mean to say that theta is equal to tan inverse 0? Because we want to know what tan inverse of 0 is. Well, theta is tan inverse 0 if and only if tan theta is equal to 0. But remember that the inverse tan function is the inverse of the restricted tan function, where our values of theta are restricted between minus pi by 2 and pi by 2. All right, well, that's the same as saying that sine theta over cos theta is 0, and theta is between pi by 2 and minus pi by 2. And the only way that this quotient will get to be 0 is if the numerator is 0. So we're looking for where sine theta is 0 and theta is between minus pi by 2 and pi by 2. And in fact, the place where sine theta is 0 for theta between minus pi by 2 and pi by 2 is when theta is equal to 0. So this is then if and only if theta is equal to 0. Okay, well, what was theta? Theta was tan inverse 0, so that is tan inverse of 0 is equal to 0. All right, so tan inverse 0 is equal to 0, and that's what we were looking for. We were wondering what is tan inverse 0, because that's the value of this limit. We just determined that tan inverse 0 is equal to 0. So we write that down here. In fact, for tan inverse 0, you might note that you'll know that tan inverse 0 is 0 if you happen to recall what the graph of the inverse tan function looks like. Here it is up here. Go back up. What is tan inverse of 0? Well, you can see that tan inverse of 0 is 0. Of course, for other values of x besides 0, to calculate tan inverse x, you would probably want to go through the procedure that we used just now, namely this procedure right here, to figure out what tan inverse of x is. All right, well, that completes this example and this video.